Now we'll talk about design philosophies, design methods or design philosophies. We have three methods of design that have been long prevalent, and working stress method, which basically started as a first design method that people used in the olden time. Even now, in fact, we are using allowable stress or working stress method design in pre-stressed to find the amount of pre-stressing. Then we check for ultimate strength. Okay, so in reinforced concrete system, nowadays we are using limit state design. We'll talk about that, what it is. Then came basically strength design or ultimate load method. It focuses on conditions at loads actually greater than service loads. Okay, when the failure may be imminent. So that's why it's called strength design or ultimate load method. And the third method, which is the prevalent method now currently being used, is the limit state design method. Okay, now let's talk about our final goal is, let's say we have load effects as S. Okay, so these are load effects. Okay, let's say load. Okay, we always want to make sure that the load effects are going to be less than resistance. Okay, so let's say resistance, basically we'll write this as resistance. Okay, so our goal is basically to make sure that the load effects are going to be less than resistance, or in other words, the resistances have to be greater than the load effects. Now, the load effects can be quantified either in terms of your internal forces, bending moment, shear force, and axial force, or can be combinations also, right? Now, what in working stress method, what we do is, okay, we look at what are the service loads. Okay, we do the analysis for service loads. Okay, and we don't use any load factor. That means I'm not going to amplify this load effects by any factor. I'm just going to take the internal forces for service load condition. Okay, but I will make sure that those load effects are going to be lesser than the allowable stresses. Okay, and what are allowable stresses? We know that if you're doing a concrete strength, let's say for FCK, that you have, we'll talk about what is FCK. Let's say concrete strength, we have 20 megapascal that we are taking. Okay, and similarly steel in the, let's say I'm taking mild steel for by design, just an example that I'm taking 250 megapascal. So for in compression, 20 megapascal. So I'm not going to go all the way to 20 megapascal in this working stress method. I'm going to limit the stresses that what I can use. Okay. And usually for concrete, we reduce the stress by one third. So if you're doing with 20 megapascal, my allowable stresses will be 20 by 3. And for steel, usually we divide it by 1.8. Okay. So 1.8 will be the stresses, the allowable stresses. Okay. So the allowable stresses for concrete is going to be one third of the actual strength, and for steel it is going to be, usually it is 1 by 1.8. Okay, of the strength. Okay, right. So that's the fraction of ultimate stresses that we are going to use to check. Okay, so ideally what we have to do, you can increase the load and reduce the resistance for good design, or you can do both. That's what we do it in limit state method, that we'll talk about it. In working stress method, what is it we do? We don't amplify the load effect. We just take the internal forces coming from service, uh, uh, from the without any load factors. But however, when the resistance calculations, we don't take the peak or ultimate values, but we reduce it by some factor of safety. And usually for concrete it is one third, and for steel it is usually it is three. Factor of safety is three for concrete. We reduce it by three, and then reduce it by 1.8 to limit your allowable stresses. Now, in ultimate load or strength design method, what we actually we do here is, again, here what we do is, okay, I'm going to deal with ultimate strength capacities of the materials. Okay, I'm not going to do the analysis at allowable stresses. I'm going to do the analysis at ultimate using the ultimate strength of the materials. But what I am doing is, as I said, load effects should be less than resistance. Okay. Now what we do here is this load effect we multiply by load factors, let's say gamma L, but resistances we use the actual material. Okay. So that is what we are trying to do. Okay. So so this is what we do. In working stress method, what is that we did? The load effects we kept, the gamma L will be 1. Okay. Service loads that we used, but resistances we divided by some factor of safety. So in ultimate load method, only the load effects are increased. The resistances we are using the actual ultimate strength capacities. Okay, so this is what we do, and we make sure that the strength provided will be greater than or equal to strength required to carry factored loads, or in other words, R has to be greater than gamma L times S, where S is your load effect. Okay, so that is what we are doing. Right. So the factored loads are obtained by multiplying the working load, service loads, usually greater than unity. So this gamma L factor is going to be greater than unity. So that is what it is. Right. And so what is the advantage with this ultimate load or strength method is you can have different load factors for different loads. For example, that is one of the disadvantages of working stress method, because it doesn't really consider the variability in the load, and in fact you will have more variability in loads than the material properties, because material properties are designed by us. That also will have variability, but you'll have more variability in loads. That variations in the load is not really considered in the working stress method. So this method allows for different load factors for load, and because you're dealing with maximum strength of the material in these checks, you usually end up with more slender sections and more economical designs than working stress method. Okay, but also if you look at the several bridges that are built by Britishers, even now they are standing. Okay, so if those are all designed by working stress method, the reason is in working stress method, because we are designing it for allowable stresses which are considerably lesser than your ultimate strength, you end up providing more deeper sections, right? So when the moment you have very thick and deep sections, usually the stress levels in the steel is going to be less under service loads. So you are going to have less curvatures, and you're going to have less crack widths and less deflection. The moment you have less crack widths and less deflection, your durability performance is going to be much better. That is why the structures that were built even 100, years ago, some of the bridges still we were using it because they were heavily over designed, and at under service loads, their stress levels in the steel and the crack widths are very limited. Okay, so that is the thing. But however, in ultimate load method, because we are using the maximum strength of the material, you end up with more slender sections and they are more economical. Again, what is the drawback of this ultimate load method? As we have seen in working stress, we deal at the serviceability conditions. We don't really check for ultimate. Here, we are designing it for ultimate load condition, but there is no check for serviceability condition. So this is one of the drawbacks of ultimate load method. So it can lead to deflection and cracking issues. Again, the moment you have deflection and cracking, again durability is compromised. Okay, so durability is compromised. That is one thing that you have to keep in mind. Right. Now we'll get so limit state method, which is the one that is currently in vogue, which basically considers both the variations in loads and variations in material properties. And it is also having different limit states that we follow in our design. Okay, so let's talk about how this limit state is actually probabilistic analysis method. It allows for probabilistic analysis and design at a lower level. We will talk about how it is being done. For example, so let's say what is safety provision. So safety is required to ensure that the structure can sustain all the expected loads during its construction stage and its lifespan with an appropriate factor of safety. Now we can ask what is that appropriate level of factor of safety. So we will talk about that. Okay, so the main reasons is there are variability in resistance. Okay, so though we design for a particular concrete strength, let's say M25, but what is the guarantee that exactly that M25 will be achieved in the site? So that is another problem. Again, steel, though it is produced in factory, we have seen that when we test steel rebars, we do get quite a variations even in steel rebar which are produced in factory, the yield strength and ultimate strength. So there is a variability in material strength. Then there are several assumptions that are made in design. Okay, so that may not be correct. Okay, and then you're going to have differences between as-built dimensions and those found in structural drawings. Again, structural drawings, you may end up designing a column, let's say 300 mm by 300. Inside, it will be 290 by 300. Okay, so what are the implications of that? So there are inherent variability in resistance that we need to account for. Then major another important aspect is the variability in loading. For example, earthquake and wind loads. Okay, we have done a lot of measurement and we have a fairly good idea how it is, but there is a huge amount of variability in the loading. And even in dead loads and live loads, okay, you end up with having quite a good amount of variability in your design. So the real loads may be differing from assumed design loads or distributed different. Okay, so the distribution of your live loads also can be very different than what you have actually assumed in your analysis. And then the next is the consequences of failure. Okay, again, so if the structural element is failing, it can lead to potential loss of life and cost of, there is a cost associated with clearing the debris and replacement of structure, and then cost overall to the society. Let's say for one important bridge is failing during an earthquake, then you lose the connectivity between two important parts. Or if, let's say one hospital has failed during an earthquake, then imagine the consequences. So the consequences of failure also we need to keep in mind while we consider the design. So this is what I talked about. I think there's going to be a lot of variability in your loading that you're assuming, and you can see that the traffic condition. If you're designing a bridge, and bridges are usually designed for 100 years of service life. So your traffic, for example, for bridges that are there in 1970s, for example, you can imagine the size of the truck and the volume of traffic. And now in 2020, definitely the sizes of trucks have increased, the load distribution has changed, and also the volume of traffic is also increased. So these variability in loading we need to consider in design. There are sometimes the structures can also undergo some fire explosions and fire accidents. Those are special limits. We need to check if you're depending upon what type of structure we're doing. We need to design for those conditions also. Okay, and degradation. So these kind of degradation also happens due to corrosion, which we'll talk about it. And then again, this is what I said. You can see there is a lot of honeycombing in the concrete. Though you may specify, such kind of sections may have very less concrete strength than actually what you would have assumed in the site. Similarly, the detailing. If your detailing is not careful enough, you end up this kind of, you see the amount of bar, they are very closely spaced. If you're using, let's say, concrete with a 20 aggregate, how that aggregate can go through this? So you'll end up with this kind of honeycombing. So these are all the variabilities in loading and site condition that you have to anticipate in your design. So that is what the probabilistic analysis and design actually accounts for. Okay, so just to again highlight, so this is basically the annual maximum wind load in kilopascal, and it is given in the x-axis. Okay, and in the y-axis we have this frequency of occurrences. Okay, how many times that this wind load has occurred. For example, let's say the variation is from right from, let's say this is zero point 0.8 to about 2 kilopascal is the annual maximum wind load distribution that you have. Okay, so and this is basically we can see that how many times that is in the y-axis is frequencies, how many times that it has actually reached this value. Okay, so you can see here that there is a good like this kind of distribution that you have. Okay, and similarly, in the next one, you can see for the same grade of concrete, let's say for 20 megapascal, what is the actual strength that is realized in the construction? Okay, and again, you can see here there is a variation, usually it follows the real-time data. Usually it follows Gaussian or normal distribution like this. So here we are talking about load variation. Here we are talking about concrete strength variation, right? So there's going to be variability both in load effects as well as in the strength. Now, we need to consider this variability. Okay, there are two ways of representing this data sets. Either I can take the frequency or all number of observations also you can say, or the probability of particular occurrence, right? So you can plot them either in two ways. The probability of number of occurrences can be plotted just like what we have here. Basically, the frequency of annual maximum wind load, it can also be plotted like this. So this is the problem. For example, if I'm taking 1.2 kilopascal of wind, what is the probability of occurrence? We can find using this, and this is, you can plot probability of occurrence of a particular wind load like this. And also this data also can be presented in the form of cumulative number of observations. Okay, so if you integrate all this p of x from the lower end to the lower limit to the upper limit, then your total probability, cumulative probability, is going to be 1. Okay, so and then you can also integrate this cumulative observations or cumulative probability from one limit to another limit. For example, here from 0 to particular x, that what I'm doing, from here to particular x, if I'm doing whatever that cumulative probability you do it, that is a value that you go here. So that is why it is increasing and then reaching a maximum value of 1 here. So the cumulative probability is taken as integral from 0 to x of particular occurrence, then you do the integration, then you get your cumulative probability. Or you just plot the number of observations for a probability in this way. Okay, so there are two ways of representing the variations in the data set. Right. So now we'll talk about it. So as I said, there is going to be variability in the load and there is going to be variability in the material strength. And now what we have to do, ideally, as we have seen in the previous slides, load effects has to be less than resistance, right? What I have to do, I have to increase this load effects by some load factors, let's say gamma L. And then what I have to do, I have to reduce the strength by some factor, okay, which is partial safety factor for material. This is what ideally we need to do, so that we account for both the variability in the load as well as the variability in the resistance, right? So usually that is what we try to do. Characteristic load, we'll see what is characteristic load. Characteristic load is a value of the load which has 95% probability of not being exceeded during the lifetime of the structure. So let's say we go back to the previous example of the wind load distribution that we saw. So for design, what we have to choose is, we have to choose a load in such a way that only 5% probability of exceedance is going to be there. So let's say this is the wind load distribution that we have. Okay, so this is the distribution that we're talking about. Okay, and usually it follows most of the real-time data, they follow normal or Gaussian distribution that we have shown here, right? And where your mean is going to be here, right? And then you usually it fits within mean minus 3 times standard deviation, mean plus 3 times standard deviation, right? So what is the load that we have to consider in this case? We want to increase the load in such a way that only 5% it will be there. So if you look at this area, this is the area that is 2.2. So I have to choose a load in such a way, this should be my load, so that only 5% of this area will be at a time that will be exceeded. So, okay, so that is what we define that as characteristic load. Okay, and okay, this is with respect to load. Now let's see what is characteristic strength. Okay, what is characteristic strength? Characteristic strength is defined as this level of strength below which the specified portion of all the valid test results is expected to fail. So unless otherwise stated, we usually take it as 5%. If you test 100 samples of cube strength, only 5 samples are expected to go below that specified value. So what we have to do? I have to choose a lower value of strength. So in that case, then what I have to do? I have to choose something here. Let's say strength. So only this is the value that I have to choose. So only 5% of failure is acceptable. So what we do? We increase the load and then we decrease the actual strength from mean strength. So here what is it? Load, what we do? We increase the effect. So this is what we do for load. So from the mean, I add 1.65 times sigma. Okay. And that is the value that I fix it for characteristic load. Now strength, what we do? This is for load. Okay. This is for strength. Okay. So load, I take a higher value. For strength, I take a lower value. Okay. So this is the value that we take. Okay. So characteristic load is the value of the load which has 95% probability of not being exceeded. Characteristic strength is what? Is this level of strength below which a specified portion of all, only 5% probability of being exceeded. Okay. Or being lesser than that chosen value. Okay. So that is what it is we are going to use. Okay, now let's look at the probabilistic analysis and design. And for structure, a structural element, the probability of failure should be usually kept less than 10 to the power of minus 5 per year. If let's say if you're designing for 50 years or 100 years, you multiply that by 30 and 30 times 10 to the power of minus 5. If you're designing for 30 years, or 100 multiplied by, right? So that should be the probability of failure that we need to take. Again, we talked about both the load effects and resistance. If you are calculating the capacity, if you plot that, it is going to follow a normal distribution like this. Okay, this is what we have. Okay, they're going to follow normal distribution. So what is that we have done? Again, I've told you for characteristic loads. Basically, if you take, we let's say this is your load effect, then what we do? We increase it by load factor. So you end up with this gamma Sn. So this is an increased load effect for a particular condition, right? Then what we do, resistance we take distribution, and then what we do, we reduce, because in the x-axis what we have is the load and resistance variables. In the y-axis is the probability density. That is basically the distribution of this load and resistance. Okay, so we reduce the resistance values and we increase the load effect. Now, if you look at it, you can have a situation, right, where your resistance can actually, because this is in the x-axis, we are talking about load and resistance. Okay, this is the area where you can have load effects can increase the load effects can be higher than the resistance values, which is not we want. So when the load effects are becoming more than the resistance values, then it is basically the it's a failure. Okay, it's a failure condition. So where always in design we want load effects to be lesser than your resistance. So in this region, if you plot, if there is a region that is showing that the load effects are higher than the resistance value. Okay, so this one. Similarly, we can also plot for a serviceability conditions. It's not only we have to follow different limit state. We will talk about that. One is for strength, another one is for serviceability. Here for serviceability, I have taken one allowable deflection. Okay, so when you start plotting this actual deflection measurements, there is a situation that the deflection can be here. If you plot deflection in the x-axis, there is an area where the deflections can be higher than your allowable deflection. So this is the region where there is a probability of failure, right? So usually what will happen here is in if for real-time data, both load effects and resistance usually follow this normal or Gaussian distribution. Then what I can do is I can also plot, there is a safety margin that I can plot. So how do you define the safety margin? Safety margin can be written as, let's say, Y, which is basically R minus S, where R is your resistance, minus S is your load effect. Always we want resistance to be higher than your load effect. So this is what we have shown in another fashion. So this all these load effects. Okay, what we do, we increase it by gamma to get increased load effect, and this is your resistance. Then what we do? We reduce the resistance to get your this. Okay, so uh, this is the resistance that reduce the resistance. Okay, and this is the figure, the same thing that we have seen here, right? And there is an area where your resistance can go lesser than your load effect. Okay, now how much is that acceptable? Is that what we are going to look at, the safety margin, where y is r minus s. If both load effects and resistance effects are following the Gaussian distribution, the difference also will follow the normal or Gaussian distribution. So when is a failure? When this, we want r should be greater than s. So when y becomes less than 0, then it is our failure. So if you plot this y, which is the safety margin, again it is going to follow this normal distribution, where I can define my safety index in such a way that it is going to be the ratio of your mean safety margin divided by the standard deviations. Or in other words, beta is going to be y bar divided by sigma y, where sigma y is standard deviation of your safety margin. And you can choose in such a way that this failure region is going to be within an acceptable value, because there is no guarantee that you are going to have absolute safe design. There is always an acceptable level of probability of failure that we need to account for in our design, but those are given by codes of practice usually. So we choose values of safety index to make sure that the probability of failure is within the acceptable value. Now, you see here, of course, when you choose beta as 0, the probability of failure is going to be 50% at 0.5. We don't want. For structural failure, we want the failures to be very, very low. So this is the value that we talked about per year. If you're using 50 years, so it's going to be 50 multiplied by 10 to the power of minus 5. And usually we choose beta values between 3 and 3.5 or 4, depending upon what type of structure that you're doing. Let's say if you're doing a nuclear reactor, then beta value can be higher as well. Okay, if you're going to do a design a simple residential building, the beta value usually is taken as 3. Okay, right. So again, depending upon the variations in the loads, the codes specify different values. If you have only dead load and live load combination, beta value of 3 is taken. If you have dead, live, and earthquake, all three of them considered, the probability of all three of them considered occurring together is is where we have considered beta value to be slightly a lower value. Okay, so there's going to be a lower probability of all the full loads acting together. So that is why the beta value that is chosen is slightly a lower value. Right. So now we have understood how this safety margin and the probabilistic features are considered in design. And now, how is the actual it is included in your limit state design? Okay, as I've told you, we are going to increase the load effects by load factor, which is gamma f here, and then we are going to reduce the material strength that we are going to use for calculating the resistances by gamma m, which is the partial safety factor for material strength. Okay, so again, we are going to do the design checks for two levels: limit state of collapse and limit state for serviceability. So the code IS 456 gives you what kind of load factor that we need to consider in our design. Okay, for example, you have when you have dead load and imposed loads that are considered. Okay, we and wind loads together, basically 1.5 for dead load, 1.5 for imposed load, and 1 for wind load. Similarly, when you have dead load and wind load together, these are the load combinations that are here. In this case, I think when you're considering earthquake effects, the wind load can be replaced with earthquake load. Okay. Now you can argue that usually the dead loads we know exactly there is a less variability in dead loads. Okay, because we know we design the thickness of the slab, we know the density of the material that we are using. So dead loads can be quite accurately calculated compared to that of live loads. However, for simplicity, IS-456 considered same load factors, but if you look at American code, it considers a lower load factor, in this case gamma f of 1.2 for dead load. Okay, because there is a less variability in dead loads. Okay, but our code is considering actually a slightly a higher uh, higher dead load factor. Okay, right. Okay, so now what is reliability? Okay, so reliability is basically expressed as a complement of probability of failure, which is expressed as 1 minus PF. And we have different levels of reliability methods. The level 3 reliability method is a full scale probabilistic analysis, and it is highly advanced and it is mathematically difficult. And generally, it is used only at the research level. Okay. And if you're designing a very special structure, very tall, let's say bridge or a very nuclear reactor, sometimes for specialized conditions, we can use this level 3 reliability analysis. The next level is a lower level, level 2 reliability, and most this is simplified by limiting the probability of information of basic variables to second moment statistic, that is only with mean and variance. Okay, but this is what the codes which are actually they use level 1 reliability method, and it is actually a deterministic approach rather than the probabilistic approach. And here we are considering the variability by accounting for multiple safety factor format. What is that multiple safety factor? As I've told you, we increase the load effects by gamma L and or gamma F, and reduce the resistances by partial safety factor for material, which is gamma M. So this is a level 1 reliability method is what the code uses. It's a more of a deterministic approach rather than a probabilistic approach. Now let's talk about what is a limit state. Okay, as the name says, a limit state is a condition of structure beyond which it no longer fulfills the relevant design criteria. Okay, we have different limit state that are there. Limit state of collapse, that we design it for strength. Of course, when we do the design, a collapse can occur in multiple actions. It can happen in flexion, it can happen under axial, it can happen under shear, it can happen in torsion, it can happen due to bond. So multiple limit state of collapse is possible, right? And we need to make sure that the structure shall be designed to withstand safely all the loads which are acting on it throughout the life, and also should satisfy serviceability requirements. Now, what are the different ultimate limit states or limit state of collapse that we do? The loss of equilibrium, of course, we don't want that, right? And this is what the material failure is, where you're going to have material failure or rupture of a particular section, one or more critical sections. You can also have progressive collapse. So this is again when you're doing a tall building, we have to make sure that the structure is having adequate structural redundancy. Even if one or two major columns are removed, the structure should still be able to stand so that people can evacuate safely. And also instability and formation of plastic mechanism, fatigue also, they are all comes under limit states. Okay, these are some of the examples of some of the structural elements that we have tested in our lab. You can see this is a beam that failed in flexure, and this is one of the research work we did. We tried to replace the steel rebar with GFRP rebar, and we put very less amount of GFRP rebar. So usually in design, failure by tension is actually preferred. But in this case, in fact, even though the member is failing in flexure, it failed in a very brittle mode. So you should really know a good understanding of how the systems work together. And this is again one of the hollow core slab. It was tested and it failed in shear. And again, shear is a very brittle mode of failure. That also we have to make sure that we avoid these kind of brittle mode of failure. And this is one of the column that we tested. You can see again the column failed under combinations of bending and compression. So when we talk about column design, we'll talk about that, right? Right. So so this is limit state of collapse. Now we'll talk about serviceability limit states. Okay. So again, the structure should be serviceable as well. So it has to satisfy the allowable deflection requirement, and crack width has to be less than a certain value, and the structure cannot vibrate. For example, you see here, this is a suspension bridge. If it is vibrating, of course, the vehicle cannot fly on that. And sometimes we also check for special limit state. Okay, so damage or collapse in extreme earthquakes, this will come under special limit state. And structural effects of fire, explosion, or vehicular collision, what are the effect? That is a special limit state. And then structural effects of corrosion or deterioration, this is also one of the special limit states. But usually we check for limit state of collapse and limit state of serviceability. Okay. As I've told you, for water tank, the crack width check will be more important than the strength equipment. In fact, your design will be controlled by crack width rather than strength. So, depending upon again what type of structure that you're designing, the limit state will govern the design. Right. So now let's briefly talk about differences in American Concrete Institute and IS code. And AC code is bases on load resistance factor design method and uses load factors and strength reduction factor. If you look at it in IS code, we also use load factors, but what we use is a partial safety factor or partial material safety factor. Here, what they do is a strength reduction factor. Again, the philosophy is nearly same, right? And they use the actual stress strain core properties of concrete and steel. And important aspect is the strength reduction factor. Actually, it depends upon what kind of design that you do. If you are designing a ductile design, then the strength reduction factor will be it is going to not penalize the designer. Okay. And if you are doing a brittle design, the strength reduction factor will be lower. So your capacities will be reduced as a penalty for designing a more brittle failure mode. So this is one advantage. So strength reduction factor in a more rational manner, it accounts for the failure mode that design engineer is designing for. However, in IS code method, we use partial safety factor. Again, we use load factors and material safety factor, and we use the design stress strain curves for concrete and steel in your design. And right, so this is what in the ACI. Again, we design for ultimate and check for service. This is what I talk about. This is your demand and this is the resistance. Of course, the resistance has to be greater than your load effect. That is what we talked about. Now, the resistance is reduced by a factor called strength reduction factor. Okay. Now, you see the strength reduction factor for bending, it varies from 0.65 to zero point 0.9. Okay. Similarly, for shear, it varies from 0.65 to 0.75. For axial, it varies from 0.65 to zero point 0.7. You can see that in bending, you have again bending also. If you're designing a column under combined axial compression bending, you can have compression dominant failure mode also. So depending upon the failure mode that you have, your strength reduction factors are changing. Okay, so this is again that one of the things that we need to consider. So AC code does this in a more rational manner, which accounts for the modes of failure that what you're designing for. If you're designing a brittle mode, the reduction in strength will be higher. If you're designing for a ductile mode, the penalty in reduction is going to be lesser. So which favors. But in IS code, we don't really consider that. We just use the partial safety factor, which is not really depending upon the failure mode, that particular things. We have other reduction factors. We also have, we reduce the strength. For example, when your column is failing in compression mode, there is a reduction factor that are there, but it does not really account for the modes of failure. So this is the thing. Again, AC code is also same like your limit state method, what we follow. This is called as LRFT method, load resistance factor design approach. And this is your demand and this is your capacity, nominal capacity, and this is reduced by strength reduction factor. Okay. And also you can see here, as I've told you, the load factors for dead load is less 1.2 and for live load it is 1.6. In IS code, we have 1.5 as a load factor for both dead load and live load. So this is some differences. Okay, so let us conclude this module 1.2. So briefly, we talked about what are the objectives of structural design and what are the various factors that need to be considered in the design, right? We talked about that. And then we also discussed what are the need for a design code. We discussed about that. And we have three types of concrete design that we usually do. One is the plain concrete, another one is the reinforced concrete. That is what this course is all about. And the third one is the pre-stressed concrete. So we talked about it. And then design philosophies and design approaches that evolved over a period of time, starting from working stress method and ultimate load method, and then limit state method. That is what we are currently using. So we talked about the probabilistic features of limit state method, the variability in loading, variability in your resistance, and how you fix your safety margin considering the safety index, which is a reliability index. Usually the reliability index of beta of 3 to 3.5 is used in design. So we talked about that. All right. So with this, these are some of the references where the material has been taken. Right. So with this, we will end this first week, the module 1.2. We will discuss the material aspects in the next class. Thank you.